Let us take a look of the chapter 7, which is the main part of the thesis. And this is try to talk about the multi-target classification. As you can see, this is in the title of the thesis. And therefore, let's take a look of the outline of what we want to talk today. Starting with the problem definition, what is a multi-target classification? It is a very important concept to understand the problem itself. And then, based on this problem, we want to look into what are the methods that we can do and how do we evaluate the results. And finally, let's take a look of the result to see does it work in terms of what we call a multi-target classification. So, starting with the multi-target classification, in previous chapters, each of the label were treated independently. So remember, we try to predict the price, we try to predict the grade, we also try to predict the region, which is the old world or new world. That is, each classifier was given in one task at a time. Each one of them are independent with each other. So as one quick image, if we want to predict all three labels simultaneously, it is going to be a much more difficult problem. So it's not going to be independent information anymore. We want to predict all three of those together. And that is creating a much more complicated space of the prediction. So instead of predicting things independently, what we want to do is predict them all, which means we want to take a look of the Y attributes information, and then we want to predict what is the grade range, what is the price, and what is the region at the same time. So don't confuse with what we call a multi-class classification. For a multi-class classification, indicating we have one label and there are multiple classes. Instead of binary classification, in our grade, in our price, there are 4 categories, and that is what we call a multi-class classification. So we have 3 labels to predict. And now let's take a look of the definition here. If all 3 labels in our example are binary classes, then that is what we call a multi-label classification. So it's still not the topics we are looking at, which of course this is under the what we call a multi-target problem. So if that is a multi-label, in our case 3 labels, and then all 3 labels are binary class classification, which we have 90 plus and 90 minus grade, and then for the price, $29 above and $29 below, as well as old world, new world. In that example, it is a multi-label classification because it's a multiple label and it's binary classes already. However, if we looked into 4 classes in grade and 4 classes in price, while we still have the 2 class in the region, that will transform the problem into a next level, which is what we call a multi-class, multi-label classification. So that's why we add a multi-class on top of multi-label classification. Or we can call it as a multi-target prediction. And therefore it has multiple label and multiple class. And that is like the most complicated form that we have in this thesis. And of course, in this topic, we want to talk about multi-label classification first as the 2 classes for 3 labels, and then we will move on to, of course, the multi-target prediction. So methods, how do we deal with this? It's much more complicated, and now we have 3 labels to look into. More importantly, each label may or may not have connections with each other. So if we want to predict all 3 things together, can we predict one of the label first and then use that information to help us increasing the accuracy, so increasing the evaluation matrices while we predict the next attribute, next label, as well as the next label. So let's take a look at the methods. Methods-wise, we have 5 methods I want to discuss with you guys in this presentation, starting with the binary relevance method, and then we will look into the label power set method, and we will look into classifier chains, basing, classifier chains as well as conditional dependency network. So for the first one, binary relevance, this is probably the simplest form. This is still using the regular multi-class problem, so that we try to work on first binary classification. For example, if the top is going to be the region, we can predict the region into yes or no, or new world or world. And then we can do the next level with predicting the grade, and then you will look into two more trees, and then each grade can keep going with the price, so that we can make this kind of binary predictions one step at a time to help us identify all three labels. Of course, by doing so, we still treat each label independently, so that we are really not really doing any extra things than what we already done. It just connects all the things together. We can still predict all three things together, it's just that we do each one independently. So this is what we call a binary relevance method. If we go to the next one, is the label power set. We try to combine the labels together. So how do we do that? We create new labels. So the value of this label is built for a combination of the original labels. So what does that mean? What we're trying to do is this one, saying that since we have three labels, starting with all binary classes, in saying that an old world wine of outstanding quality that costs $51 would give a label, and that corresponding to the old world outstanding price quartile 4. And then where the new world wine outstanding quality costs $12 would be given a label value that new world to outstanding and price quartile 1. What they're trying to say is that we create all possible combinations of the labels and then number them. So saying that if this is a 0 to the region, 0 to the grade, and 0 to the price, then we can create our first label, which is the very first label. The next label can be 001, that's our second label. And the next one can be 010, this is going to be our third label. 011 be the fourth label. So that is, if all the labels are binary, then we will be able to create 2 multiply 2 multiply 2, indicating 8 different labels, so that we can merge all of those things together. So we transform from 3 labels into 1 label, but this 1 label has all combination of the values. So we will make it become 8 classes if the 2-class problem for grade price, and each label has 2 classes, so that would be 8 classes. Of course, if we look into the multi-target problem, so we have 2 classes in region, 4 classes in grade, and 4 classes in the price, then we will end up with 2 multiply 4 multiply 4, creating a 32 possible combinations. So we have 1 label with 32 classes. And of course, this is going to be much more complicated, but look on the other side. Each label will create a combination of the 3 things together. So this will have the potential to capture the connections between the different labels. So a multi-class classifier such as SVM using 1 versus 1 approach is then trained by this new label, and that's one of the methods that we can do. The next one is what we call a classifier chains. So what they're trying to do is that it will connect the labels together. So it attempts to preserve the dependencies between the labels while still using binary relevance. So what they're trying to do is that in the first stage of the classifier chain, so we are not going to do something special. We try to predict the first label. And once we will get that first label, we use that predicted information. This classifier will make predictions for the next instance, for the next label. So for the second stage of the classifier chain, the first stage predictions are made an independent variable, an input. So we want to take that prediction as an input. So when we do that, we will have all the attributes plus the predicted information, and then we try to predict the next label. So for example, if we are try to predict a y, first of all, say that we're going to use the region as our first prediction, since it has the best performance. So what we can do is use all the attributes to predict the region, and saying that the first one is coming from the old world. Then while we try to predict the next value using talking about the grade, then we can use all the attributes plus the region that we predicted, and then we have actually like one more attribute to consider as the input to predict the grade. So once we predict the grade, we then, to predict the price wise, we can have all the attributes plus the region plus the grade information. So you can see that we can use what we have predicted as an input to predict the next label. In this case, the order do matters. So remember why I want to put either region or grade as the first predicting label, because usually if we can have a better prediction accuracy, we have more confidence in what we have been predicted, and then get more accuracy to more accurate attribute information to predict the next one. So the order of the label prediction do matters in the classifier chain. So you can see that what this is trying to do is that using attributes to predict the first one, then what we want is using the attribute plus the first label to predict the next one. While we try to predict the third label wise, we have the information from X that comes from the second label as well as the first label. And when we try to predict the last label, we can have all the attributes plus the first three prediction labels to help us make the judgments on the last label. And that's what we call a classifier chain here. The next one is Bayesian classifier chain. So in this one, when you see Bayesian, that means there's some probability concepts coming in, like our Bayesian networks. So in this case, Bayesian classifier chain are another classifier chain methods which using the same concept. We can use what we predicted as part of the input to predict the next label. The basic difference between the Bayesian classifier chain and classifier chain is that BCC, Bayesian classifier chain, are not fully parameterized, while CCR, what they're trying to say is that in BCC, instead of using all previously predicted labels, maybe only some of them are working. So I want to pick several of those what I consider as more related, more relevant predictions as the attribute for predicting the next one. So that is, BCC do not necessarily use all the labels in the previous stage to classify the next stage label. The sparsity in the connections between the labels lead to a faster, because we have fewer trainings, and then potentially a more accurate, as label which do not have dependencies between them do not need to be linked. And therefore, if we look into the figures over here, you will be able to see that when we try to use X to predict the first label, we get the information. When we try to predict the second label, we consider all the attributes plus the first predictions to here. When we try to predict the third label, you can notice that Y1 did not provide information. We use Y2 plus the attributes to look into the Y3, while Y4 has only taken the attributes plus the Y2's input. Of course, how do we link all of this is going to be an interesting topics, and there's going to be, we can play those values around. You can see that this is like a subcategory of this one, while this one, we have all the weights on each line equals to 1. In this case, some of the lines have the weight of 0, and they are not providing the information. So that if we don't think they are relevant, then we don't connect them. Therefore, you can see the next one, what we want to look into is the conditional dependency network. It is using the similar concept, but instead of 0, 1 in the weighting, we can give the probability. So maybe this one weights 0.5 to y2, y2 to y3 has 0.8, y1 to y3 has only 0.1. So we can add the weight into each lines of those and then try to make, hopefully, a better prediction. So that for a conditional dependency network, as I mentioned, we add the percentages, we add the probabilities in each line that connects them. So a CDN is made by forming an undirected, fully connected graph between the labels. They are all connected to each other. The only difference is that there's weight on each connection, on each lines. CDNs encoded the dependency between the different labels. This is done by training as many binary classifiers as there are labels, where each classifier defines a conditional probabilistic distribution on one label given all other labels, and then input attributes. So that this is the figure I found from the original paper, which I think it provides a better information. So you can try to predict Y1, first label, second label, third label, fourth label, by using all the informations coming from not only the X as the attribute, but also other labels, and then they are weighted on each one of those. So that this is kind of the most complicated one to connect all the predictions together, and that is what we call the conditional dependency network.